So I would like to thank the organizers and the scientific committee for organizing such a wonderful meeting and for giving me the honor of presenting my work here. It's my first time in Costa Rica. I'm very pleased to be here. I really enjoy the atmosphere of the meeting. I was the chair of the European branch of ASL for many years, so this is the branch that's in charge of organizing summer meetings of ASL, where the atmosphere is a little bit like the one here, people coming from all the different countries, etc. And I'm very pleased to see the same atmosphere here in Latin America, which is, I don't think everywhere in Latin America, only in a few countries. And I hope that I will continue this nice connection that we developed during those visits and during these conferences. So my title has changed a little bit, but that's just because it's just quicker to type it that way. It's actually the same topic that I wanted to tell you about. And this topic somehow fits in what we have already seen. We have seen two very long tutorials. There were two that were actually connected to what I want to talk about. One is the tutorial on pseudo-finite structures by Dario Garcia. And the other one is Osvaldo Guzman's tutorial on constructions of fields. And so what is the connection? So let's see what is this all about. In fact, this is somehow a large project which has to do with studying properties of large infinite structures. Large here just means of the size of the perhaps first and half by considering how such structures are built from finite fields. So I'm going first to start with some general remarks about this type of thing. Various ways in which people have been studying this, and what is it that people have brought to it recently. And then I will talk about some of my own work. So the point is that so this here is the project which kindly pays my salary and which finances my work. This is a project from the European Union which is called From Finite to Infinite. And the point of this project is to study the passage from properties of finite structures to infinite structures. And why would one do that? Well, to hope to get some transfer of properties. So these properties could be different things. It could be, for example, Ramsey degrees. So this Ramsey degrees, for those of you who do not very quickly combinatorics, this is kind of a generalized version of Ramsey theorem, in which you allow not just monochromatic sets, but sets that are homogeneous and have small number of colors. Some graph theoretical variants, logical properties, algorithms, and similar. And this also has to do with a project on the way, which is to study effective properties of structures of size alpha. So the work that I will talk about most today, I will talk about one project of mine and two results. One will be about classes of nice structures of size alpha 1, which is a joint project with Wiesław Kubisz in Prague. Some results of this program are represented by these couple of papers. Just to tell you how these things come from different directions. One is about graphones, and this is something that connects very much to what Dario was telling us about in this model theory of pseudo-finite structures. Graphones are sort of outer products, but outer products with a measure. So they are like the law of measure. They were discovered completely independently of us in logic. They were discovered by people in graph theory, by Lovash and his group. These are uncountable structures, so they are precisely continuum. that are approximated by finite structures, in the sense that you have a countable sequence of finite objects, graphs, graph-forms, that converge in a certain very special way to a measurable function from the sphere of the unit integral to 0. Because of this connection with the outer product that was discovered by electrostaticity, these structures lend themselves to methods from logic. And in this paper that they published this year, it's a paper that Mirna Dzamonja, a model theorist from London, we looked at graph forms that arise from graphs which are definable over finite fields. So many people here work in that subject. And so what we did in this is to look at power regularity levels, which certain people in that subject know, and we prove it using graph forms. This lemma was originally proved by Tao using methods from harmonic analysis, and it was improved by Kina and Starchenko. Unfortunately, they didn't publish, but the papers available very nicely these pseudo-finite structures. And then we proved it using graph forms and obtained better bounds. And in addition, we were able to use our technique to talk about asymptotic classes and other classes. So that is this project. And here another project is about length degrees, again about outer products. Again, connecting to the tutorial that we had. Look at an outer product of finite structures. If, for example, take some finite linear orders or something, and then you look at the colorings of the outer product, and you ask yourself, does this have any magic properties? And so what we have been able to do in this joint work with Anna Bartoshova, Anna Patel, and Wim Sko, which is still in preparation, is to prove that if we start with finite objects that come from a class that has a small relative degree, then the outer product has a small relative degree with respect to internal colorings. So I think this is what I know. The first time that people look at colorings of outer products. So let's see what else is there. I mentioned some algorithms in my first slide. So I want to say a few words about the interest of people in computer sciences in this type of projects, because we have here colleagues who come also from computer science logic. Of course, infinite objects are studied in mathematics as much as in computer sciences. We all know about Turing machines, automata. But then maybe we get into things that are a little bit more into computer sciences, termination processes, infinite words, and something that they call small infinite sets. So these are infinite sets that are constructed in a very controlled way. And why do people in computer sciences study this? Why would you want to study an infinite object if you just work with a finite computer? But the thing is that you actually never work with a finite computer. You work with the set of all computers, which is an unbounded class of things which is dynamically being increased over time. So in fact, the interest is to study unbounded processes. So in a sense, they study infinite objects which are sort of potentially infinite, like before counting. Well, of course, in set theory, we also study infinity, but much more the actual infinity that is given. We start with saying, let us start with an object, given object of size R1, blah, blah, blah. So these are sort of two different ways to look at infinity. And part of this project philosophically is to join these two ways. So what is actually new in the recent approach to the connection between finite and infinite is that I think that in the past, let us say the time of Erdős, and others, people looked a lot into finite and infinite as a globality. So question could be, how do we reflect some property that we know holds of all finite structures to some property that will hold of all infinite structures? So from the actual finite to the actual infinite. And this well, it's very ambitious, and not that many things actually carry over. Those of you who come from who like to read things that were written before they were born, there is this very nice book, actually, which I well at that time, but I was also not around who was present at this conference, but this is a book that represents that type of approach, the big conference in finite and infinite combinatorics. So a new approach is to take the processing to the account. So if you remember what the Svaldo was telling us about these construction schemes, it's studying objects that are of uncountable size, but sparse, but we know how they have been constructed. So not only that we know that this object can be approximated by finite objects somehow, but we know exactly how it can be approximated. And that tells us what. Of course, it reduces the class of objects that we are studying, but it gives us in general tail structures. So we can say that there is some general feeling of studying limits of finite structures. So how these limits are taken could be of different ways. It could be ultra products, it could be graph forms, it could be construction schemes, it could be Morrises that I will mention, but it could be the Fuzzy limits, of course, which can be mentioned many times, which are popular objective study, both in set theory and model theory, and in other subjects as well. So, but in all of these contexts, we actually look at the large object as being built of finite objects in some controlled way. And I mentioned this idea of small infinite sets. This is the bridge that is used by Bojanczyk, computer scientist, of course. So he has a very nice book called Small Infinite Sets. These sets are something very familiar to model theories. These are countable structures that have a very controlled set of automorphisms. But they actually, he came to study them from data register automata. And also he models them with some other old-fashioned, to us in set theory, old-fashioned set theory, which has now been revived. This is the set theory with Ur elements. So I find it very interesting that these ideas somehow circulate between the various parts of logics. So what is common to all of those ideas is that the limits of finite structures in general could have one of three possible sizes. Of course, L0, L1, which is sort of less easy to get than L0, and also less easy to get than the continuum. So the continuum, of course, the outer product will have the size of the continuum. Morrises and construction schemes will give you L1. So another circulation of ideas, you know, people in computer science think of these and NLP, and we think that we have also been studying that problem very hard in our way in the continuum hypothesis. Anyway, so now about effectiveness. So that was something about effectiveness was in my title. So this is still on the motivation for doing these things. What could one get from the point of view of set theorists in studying this? Of course, you could get many nice objects, as we shall see if we construct them. But also, we could perhaps get a theory. There is a kind of missing theory in set theory. So we have a very strong descriptive set theory of Polish spaces. This is something that has been developed since the 30s. And this has spread itself, has links, and it has gone into ergodic theory, into all kinds of classification problems in various parts of mathematics. It's a very successful program. But because it deals with polar spaces, it is necessarily bound to something separable, countable generators. So now, how about you have the ambition of classifying non-separable objects? Something that has some Aleph1 inside, something uncountable as a generator. Then we would hope to develop an analog of descriptive set theory on the space 2 to the omega 1 to 2. Now, you want me the first one to think about this. People have thought about this and have had success, but unfortunately, it's not so easy to get descriptive set theory in that context because many things that you would expect involve not hold at all. So basic theorems of descriptive set theory, and you apply them in this generality, they do not hold. So how could we perhaps try to approach this in a different way? So we could perhaps start asking, what does effective actually mean? So I have just explained that for us in set theory, effective is described by descriptive set theory. Descriptive set theory starts with the continuum hypothesis, of course, because the continuum hypothesis is true for closed subsets of the reals, as Cantor and Bertelson told us, and this gives us then various hierarchies for region of nice sets, countable unions of closed sets, which also have CH, and then we obtain this hierarchy, border hierarchies, etc., analytic, projective sets. And this is actually put in connection with Turing compatibility, and this is effective descriptive set theory. The presence of several specialists, including my chair. Descriptive set theory is so there is really a lot of success in this. And it is connected with Turing compatibility. So if you want to lift this to omega 1, this beautiful classification method that we have for Polar spaces in the examples of Polar spaces, Cantor space, R, etc. For the Baire space, for all of sorts of unexpected examples. And the point is that we have this idea of order reduction and completeness. And this was in Omar's talk, he was saying that some problem was very hard. And then people asked him, why is this hard? There was some classification problem that he wanted to point out to us that this was hard. And the descriptive set theory might give you an answer to this type of question. Because it's the kind of answer you might get from descriptive set theory applied to a certain concept is to say, no, this problem is complete in a certain class, and therefore it's hard. So, so this is really very powerful. So how about omega 1? And this is like complexity theory, of course. So Aleph 1 is actually fails many things, not just descriptive set theory. What does it fail? It fails basically everything. It fails the compactness theory. This is the biggest failure. So if we look at L omega 1, so it's like restore the logic let's allow countably many quantifiers and conjunctions, then the compactness theory is absolutely false. In fact, the first cardinal kappa such that kappa is compact, kappa compact is a large cardinal, it's a strong cardinal. So, we are very lucky in terms of that. As I said, the analog of Ramsey's theorem fails. So, probably most people know Symposium's theorem from the 30s. So, there are some spectacular further results, notably a result from the Nordrich that says that you can color the pairs of omega 1 into omega 1 many colors, so that every uncountable set gets all the colors. So, this is the diametric opposite. So now I mentioned this analog of descriptive set theory. Of course, the analog of Koenig's theorem fails, that we know other scientists exist. So Arrowsine 3 is an uncountable tree with no uncountable chains or antichains. And so we don't really have this effectiveness notion. So what could we do? Maybe we could be more modest, and rather than looking into some sort of generalized descriptive set theory, which would be a parallel of Turing machines, maybe we could look at some simpler machines, which are automata, or we could concentrate on families of nicely built sets. So this first concept has been discussed, as I mentioned in this tutorial. But this other concept of different notion of effectiveness is something that I started studying. Building automata that will give us a notion of effectiveness rather than Turing. So let me show you one of those automata. So what's an automaton in general? You know what's a finite state automaton. You have some finite number of states. You have connections between the states, which are given by some sort of program, and you are producing breaks. So every time that you go from one state to another, you have a letter of an alphabet, and then you look what a successful run is when you start from the input state, which is unique, and you end up with one of the described final states, and the language of the automaton is all the breaks that you take in this way. Okay, so this has been studied in the finite case. They have been studied also in the case of trees. So very famously, we studied tree automata. But interestingly enough, people haven't studied automata that are built along trees that have height more than 1. So Rabin in the 60s had this very celebrated paper about trees which looks like a counter tree. Automata that obtaining some decidability results. In 1976, Sahar published a paper in journal Annals of Art, in which he solved a famous problem and asked a famous problem which is still open. So I can tell you what the famous problem is. It's still open for descriptive set theories. It probably don't know. So it is, if you look at the monadic set theory, monadic the second order logic over the reals, but you let the monadic quantifier only use Borel sets to decide. Basically, if you can correct it with some sort of automaton, it was decided. Okay, so this is the line of thought. Now, this is how an automaton looks. How about studying the automata on more complicated trees? How about studying the automata on Arrowsine trees? The point about Arrowsine trees is that they have countable levels. If you have uncountable level, that is, you are dead. It cannot be. It is wrong. You cannot have it. But if you have trees with countable levels, then it's perfectly reasonable to study this as kind of notion of effectiveness. So you would have this automaton which runs along the tree, and you have to decide what's acceptable. So here you have to go in notation. You can imagine just this process going along the tree. And the point is what to do at the limit stage. What jumps out accepted for a limit stage. So you have some choices. And that gives you an Arrowsine tree automata. So I had this idea of studying this, but I said to myself, I should simply first go to Salomon and ask him if he ever studied this, because it would be reasonable to think that he has done. And it's very interesting, no, he hasn't, but he thought of it and started writing some notes in the 1980s to study automata on generalized trees. So I sort of take it as a proof that the idea is not completely stupid. So anyway, so I'm now studying these Arrowsine tree automata, and probably there will be some joint work with it. taking into account what he did in the 80s. So these are the kind of questions that people ask in the automata theory. So is the emptiness problem of such an automata decidable? Can you associate the non-deterministic automaton and deterministic one, which has the same values? Can you associate another set second-order formulas automata? And why is this interesting to set theorists? Because if we get some positive answers, then this would give us a good notion of effectiveness in this generalized wave space. You could say that the subset of think just of the zeros and ones. So imagine that your Arnstein tree is a binary Arnstein tree. And fix such an Arnstein tree, and to say that a subset of the sequences of length omega 1 of 0 and 1 is nice if it can be produced as a rank of such an automata. And then you get a family. So these families are usually closed other unions. Yeah. If you are very lucky with your definition, they are also closed other complements. So you get some nice family. This is not the Borel family, but it is some hierarchy of nice sets. So that I mentioned. And well, why stop at the Arnstein trees? Think of Susan trees. Susan trees are even nicer. They don't have any uncountable chain on the chain. They have a small problem, they don't exist in ZFC. But there are friends doing computer sciences and selling this for millions. I'm very interested in metaverse. You know, I don't know about Latin America, but the European Union has invested an enormous amount of money in the metaverse without having any sort of definition of what this metaverse means. So you can see, I'm sure that in the United States they do this as well. You know, all kinds of definitions. Metaverse is when you have a computer in this context talking to a computer to another context, and something like science fiction. Well, but in logic, we already know what metaverses. It's when you have objects in two different universes of set theory talking to each other. And if you want a computer, then you might start with an automaton. You might start with an automaton that is supposed to be running over a Sussman tree. A Sussman tree doesn't exist. Never mind, you are constructing it at the same time that you are using this automaton. So you're constructing it by forcing it. You're talking between these two universes, and we have a perfectly good way of describing this completely scientifically, not by science fiction, but by forcing. So this actually can be very interesting in theoretical computer sciences or metaverses. So now let me go from these things which are projects, ideas, to some concrete things that fit into this context. I will no longer talk about automata, I'm going to talk about Horaces. So we changed the setting a little bit. Now go into Horaces. What are Horaces? So we are leaving now the world of descriptive set theory and the world of theoretical computer sciences. We are entering into the world of combinatorial set theory and its applications. Horaces are another way to build objects of size alpha through finite approximations. For those in the know and those who have been listening to Osvaldo, maybe the best way to say this in one sentence would be to say that these construction schemes are sort of a way to formalize in ZFC the kinds of things you might obtain by adding L-form and equilibriums, while Horaces have been used in contexts that we know how to do things by adding one. But Horace has nothing to do with forcing, it's a ZFC object. Which can be used if you add to it some forcing ingredient to construct objects, such as a solution. This study started in Jensen's work on the construction of the universe. This paper in 72, when he introduced many concepts, including Horace's. The name is well chosen, they are very messy. And in general, he wanted to study two cardinal transfer principles. So their purpose was is to build an object of, say, kappa plus n by using approximations of size less than kappa. And as n increases, this gets more and more complicated. So such a thing is called the kappa n models. Because they're so very complicated, apart from some very notably by Charles Morgan, they haven't really been used very much in concrete constructions. But except in this very simple case that it mostly interests us, which is to construct objects of size Aleph1 using finite approximations. And in this context, one can use something that was defined by Doug Velleman. It's called simplified Morris. So it's not an object that's equivalent to a Morris, but it exists if and only if the Morris, Jensen Morris exists. And it's quite, and in this particular case, omega 1, it just exists as ellipse. So what's a Morris? It's just a nice way of organizing finite approximations to some uncountable object, just as ellipse. So let me give you this definition. It's going to look a little bit messy. So what I'll do, I will put the whole definition there. And then I'm going to draw a picture of this object on the side to tell you what it is. So if you know what phrasing constructions are, it's kind of similar to that. So phrasing constructions, let us bring it here. Phrasing constructions. Works like this. You have a bunch of finite structures of some, let us say, relational language, and these finite structures have an amalgamation property, nice amalgamation property that maybe we can illustrate in this way. You have two that sit like that. You can find the third one by being allowed to move by functions that is still in this and that invests something like that. Okay, and the theorem of Frege from the 50s is that if you have a family of finite objects that satisfy the cycle of amalgamation and a couple other axioms, then there is a unique limit of that family, which is called the Frege limit. We have been studying this ever since. It's a very nice way to construct counting infinite objects. Now, these Morrises are like that. But they are going to construct objects that live on omega 1. So think of this omega 1, our final object, our limit is going to be an uncountable object, which we are going to enumerate on omega 1. And we are going to have approximations, but they're not going to be as free as those approximations here. They are rather going to be organized. They're going to be finite, but organized in omega many levels, in omega many levels. So usually, so these are some finite ordinals. That's called theta alpha. And we have some amalgamation. But the amalgamation also is less free than it was in the case of Frege. The amalgamation is done by some prescribed sets of functions. So between every alpha and beta, we have some set of functions, f alpha beta, which carry the structure of theta alpha to theta beta. And this last level is called theta omega. So we equally have functions that go from alpha to omega. And all these functions commute. So you have various commuting conditions. Like look at this number 4, it says if you fix 3 levels, then the functions that go between the smallest and the biggest can be decomposed to the value in the middle. And there is also an amalgamation here on 6. So this is basically what the Morris looks like. It exists, such Morrises exist in ZFC. I'm going to show you how you can use such an approach to construct something. And Then you could also study objects that are built along such a thing. For example, imagine you want to study some graphs. So you give some structure of those. You give to those the structure of the graph, and then you ask yourself, what is the graph that I can from this last time? Maybe there order, it could be anything you like. It could be algebra. Okay, so in this work with Kubish, we look at this is a digit galaxy, and we can also think of helping ourselves in these constructions by some forcing object. For example, a real. So a real is some function from omega to 2. And so the idea would be you are going to construct something of size alpha, and you do it by putting structures in a coherent way along these approximations, and you make your decisions like on the alpha stage, you use R of alpha to tell you what you do. So in that way, you can use a generic case to help you with these instructions. I'll show you it now. Okay, so you can put this in sort of axiomatic way. So you look at classes, you have a class of finite structures, C, and you have a class of structures of size alpha 1, in which objects of size alpha 1 were constructed using the approximations from class C. So in the formality of mathematical notation, look like that. So you could look at the whole class of objects that you can build that way and try to make some general conclusions about it. So like people look at basic constructions and what can we say of all basic constructions. So that's in this paper with Gershwin, that's what we are doing. So this is formalizing what I just told you. We fix a modus and we look at all structures of size alpha 1 that have been constructed using this method. We call it MK. So what can we say about everything that is in this MK? What do all these structures have in common? Actually, a lot. So the first thing is you might wonder if this depends on which modus we choose. So we might have two different moduses, and then each one will give us a class of countable objects. Are these classes similar? In fact, it turns out that the class doesn't depend. If you can construct an object using one modus, you can construct it using the other modus as well. So this is actually quite robust, which is stated in this theorem. So the fact that this is much more organized than the physics might make you think that this organization is really a part of what you get in it, but it is not. So let's see what else we can say. Let us see the connection between these two. There is actually a strong connection between them. Okay, so it turns out that actually these modalities are a factory of obtaining homogeneous objects because they are in a very strong way connected with the Fresnel. In the sense that you can actually, once you have an object like that, you can find a filtration of the object, which in that notation is denoted by delta, such that every countable model with this filtration X is actually a Fresnel limit of the same class. So they're all homogeneous, and this means that your final object is also homogeneous. So this means that this is a nice way of producing homogeneous structures of size alpha. We have some applications that we have started. Well, this is a this solves an open problem. So an antimetric space. What's an antimetric space? An antimetric space is a space that's ZX without let's call it D. But this D is a very related subject. It's not a metric, it's an antimetric in the sense that in every triangle there is the longest sides whose length is greater or equal than the sum of the two lengths on the side. So here, for example, this would be longer than the sum of this. And the question was to insert homogeneous things of that kind. And it was known that you cannot have them of size C class. It wasn't known that you can have them of size Aleph1. And using this type of construction, we obtained one. Let me show you something a little bit more involved, in which we actually use the forcing extension. Okay, so this is. Yes, I should also say that this fact that it's connected with the physical constructions also gives us a way to study the empty properties of the objects that we get as the first. So this is unexpected because it's not expected that objects of size omega 1 will have any density properties, since generally they don't. But if they are constructed in this way, they do, because they come if the Fraser class that constructs this and delta has length degrees, then n delta has length degrees. This is something that has been well understood, starting from a very celebrated paper by Catris, Vestal, and Dorchard. So, since this is a limit of such an object, then this also will have length properties. Very nice. Okay, so now I said that this modest construction is often very useful in connection with having one point value. Well, even the first result about modestus, this was the paper of Ellerman, he reproved the theorem that was proven by Saborcella, which is that one point real adds a system. So he proved that using Moras's by constructing the system tree using the Morris and the count. So there have been a few constructions like that, and I want to mention one that I did in 2015 about Banach spaces, just to show you how you can push from this very combinatorial thinking to something that is quite deep in mathematics. And also I should mention that the other reals, the connection of having one real, which is not the point real, but something else, hasn't really been studied. And I'm sure that there are some that I still have studied. So what I'm going to mention now, will perhaps remind Christina of her work with the Koshmet and they are into isomorphic embeddings of Banach spaces, and they proved some non-universality results in extensions by Aleph-2 point reals. So this work that I have done in 2015 is connected with that. It shows that by adding one point real, you add a non-separable Banach space, which doesn't embed into any Banach space of the same type, which comes from the ground model. And in addition, you can define this Banach space to have some nice properties, which are stated in this theorem. So, in fact, the methods that people have been using, I mentioned the Christina and others, to construct nice Banach spaces is to construct a Boolean algebra, then take its tone space, then take the space of continuous functions on this tone space, and then you have Banach space. So everything boils down to constructing a nice Boolean algebra. So the theorem here is that when you force with one point real, you add a Boolean algebra such that in the extension, this Banach space that you obtain in the way that I just mentioned is uniform legato, normable, whatever that means. This means that this small space is an uniform Eberlein contact. This is the theory. So let me see how you will do it. Okay, so now you already know that if you don't care about uniform Picasso and whatever, you don't need to know anything of that. You just need to know what's a Boolean algebra. So you're constructing a Boolean algebra using a Morris. In fact, you are not going to construct a Boolean algebra, you're going to construct a set of generators with nice people. So I was going to in some elements of this proof so you can see how this can be used perhaps in other contexts. So what we're going to do is to construct some first order structure. You have a length with two symbols, less or equal star and d. This less or equal star will be partial order. D is going to be D stands for disjoint. So symmetric and anti-reflexive. And the statement dxy and less or equal xy are constant. So you may think of that as less or equal star is like the order in the Boolean algebra, you have one element to another, and disjoint is like disjoint. And what we want to obtain is some model of that sentence, or some sentence. That sentence is trigonometric one. And then we interpret this as Boolean less or equal and B as the disjoint consideration. We generate by this I, we generate the Boolean algebra freely except for the relations that are I, and that gives us the Boolean algebra. And why is this possible? It's possible always to construct such things because of the compactness. So, and everything that you do is consistent with the absence of so the main point is to obtain this non-embodibility of your Banach space to the Banach space from the ground model. So let's see how to do that. So suppose you have this Banach space of density of 1, you take the dense set, and what we're going to guarantee is the following: whenever we have n star a number, and we have some function from omega 1 to omega 1, we'll find n star square many, which on the one hand are telling us that the norm of this sum should be n star minus less than n star minus 1, and on the other hand are telling us that the norm should be larger than n star minus 1. So in fact, we don't have a limit between the two, because any potential betting satisfies this. We are in the context of Banach spaces, so the norm in the betting is controlled by some constant n star. It is that norm of t of x is less or equal x star of x and greater than 1 of x star of x for some x star. We're just going to keep this in our construction. So what we need is boils down to controlling these kind of things. You control your bettings from omega 1 to omega 1. And point waves are very good for that. So we need to guarantee like this. And this works because of this very nice lemma about point waves, is that in the point wave extension, every function from omega 1 to omega 1 to k, or whatever k you want, in the extension is actually on an unbounded set equal to a ground model function. So that's why this partition relation actually guarantees that you can do things. Okay. So perhaps now that I think I'm just ready to make a conclusion. So the conclusion is that if you look at just about process, in fact, in general, in this context of building models nicely, the idea is that you, on the one hand, you have rich possibilities of building objects of size alpha, and on the other hand, you have methods to control how these objects are built from finite pieces. And I have given you some examples, my colleagues have given you other examples. There are things coming up all the time in this subject, like just today. that multiplied by something different by now with some very interesting topological spaces with this idea of finite approximations. So I think this idea is nice. And as far as this fast MK goes, it looks like it's an uncountable version of these nice countable models that Voyager designed. And of course, you can ask many questions in this, and are really very questions to ask. The knowledge of basic constructions, connection of this with games, some very nice games that are connected to basic constructions. So we will these games connected to models. So I think that's all. Thank you very much.
Actually, I have two questions. Well, more than two. Okay. So the first question was going back to the Einstein tree automata and so on. Are there certain absoluteness issues with those Einstein? Do you have to specialize them, or how sensitive are they? That's one question. The other one is more difficult to phrase. So you have this description here of your walls of K or as for K as nice versions, also size like one, but somehow are like nice countable models. And this brings to mind the something we have seen in stability theory and also in logics where you look for round numbers. Somehow the other ends seem to play the role of small models for all these or arbitrary large models. And the whole point, using first order stability theory, is to bring down descriptions of large models into Aleph one, but maybe sometimes Aleph 2, Aleph 3, Aleph n coming to the picture. Once we get the whole, all the Aleph n's, we somehow are able to push all the way up. This brought to mind something that's it's a pity that Artyom Chernikov isn't here, because he has this general idea that stability theory so far has been essentially one-dimensional. All properties are really about one that can reduce it to two-dimensional relations, like order property to one dimension. And he wants to push that up to n, and inspired by what's happening with n objects, n categories, n whatever. And this suggestion might want to do these morasses trying to push up nice objects. Perhaps not just to Aleph 1, but to Aleph 2, Aleph 3, Aleph n, and thereby get a hold of the really larger orbits, or does it stop at Aleph 1? Is there something in here, or?
Okay, so let me answer the two questions. The first question was how sensitive Dzamonja tree automata would be to the circulated universe in which we find ourselves. We don't think they should be, but perhaps something will come up. So this is a very big answer, but we haven't come up with anything that. Of course, the properties of the class of all Dzamonja trees are different from one universe to another. Right, and this might somehow enter into the picture once you understand the spectrum. But the other part, I do understand the perspective. And I think this actually connects to your work with abstract elementary classes, because abstract elementary classes are a way of building models of a certain size, which tends to be somewhat accountable cardinal. The L lambda plus 3, let us say, by knowing something about approximations that are smaller. And this would, on this context, be like, let us try to build objects of size R2 by knowing not only countable approximations, but also finite approximations. And I think there is potential in this. I don't think that anybody looked at it, but I think there is a big potential in this. It might be interesting also to see the connection to what people effectively have been trying for the last 10 years, is to develop efficient ways of forcing objects of size
So in the analogy with the freestanding limits, like, is there some Morales construction that you would say like is the analog of the random graph? In particular, like these random graphs, these.
So, well, I suppose since we get some homogeneity here, you just put, if you manage to put a cofinal sequence of finite graphs, so every finite graph invests into one of them, then the object that you will have here will be something that is fused every time you pattern that the possibility to be around. So that's what it is. So that's quite simple. What is more complicated will be to get the random graph in which you have the dependence for countable. So the random graph is characterized by the fact that where the two joints finite sets, there is a point this is connected. So point there and one point here. So that you can get easily, but if you want this countable, then the existence of such a thing of size omega 1 is really equivalent to CH.
Thank you.
Anything else? Well, our session coming soon, so I just before that, thank you again.
Thank you.